This is GCSE Physics Lesson 14, and this one is the principle of moments. So the objectives are to solve more complex problems using the principle of moments and to calculate missing forces or distances for a body that is in equilibrium. Equilibrium just means balanced. So what is the principle of moments? When an object is not turning, for example balanced or in equilibrium, the total clockwise moment must equal the total anti-clockwise moment. So whatever's going clockwise must be balanced out by whatever's going anti-clockwise for the system to remain in equilibrium or to be balanced. So here's an example. So we've got weight 2 and weight 1. Weight 2, if we go from the pivot, would make the body rotate clockwise, and weight 1 would make the body go anti-clockwise. So it makes sense that these two, for it to be balanced, these two moments must be equal to each other. So clockwise moment must equal anti-clockwise moment. And remember from previous lessons that moment is force times distance. Or in this case, the weight is a force. Weight's measured in newtons, remember. So W2 times distance 2 will be equal to weight 1 times distance 1. So let's do some examples. So let's try this one. If you want to pause and have a go, and then I'll take you through how to answer it. And I'll show you a good way of setting it up as well. Right, so here we go. So we've got Mary on the left, and she's got a weight of 600 newtons. So that's down, that's 600 newtons. And then we've got John on the right. His weight is 200 newtons. So she's at a distance of 1.5 meters from the pivot. Obviously this is not to scale. So there's the pivot. So apparently that's 1.5 meters. So the question is asking how far away will John be? So the two turning effects, the clockwise one created by John, I'm just going to say that John would go clockwise and Mary would go anti-clockwise. So what I'm going to do is this. Hopefully you find this helpful. I'm going to make a little table, and then I'm going to say the sum of the clockwise turning effects must be equal to the sum of the anti-clockwise turning effects for the system to be balanced or in equilibrium. So clockwise is going to be, we've got 200 newtons times D, so 200 lots of D, is equal to the anti-clockwise, which would be 600 times 1.5. That's all we need to do. So 600 times 1.5 is 900, so it's 200 times D equals 900. Then we just need to rearrange to find the distance. So to get the distance, we've got times by 200. We need to get rid of times by 200. So we do the opposite to move it to the other side. So the distance will be equal to 900 divided by 200. So the distance is 4.5 meters. Pretty big seesaw. I don't know if I've seen one that big. Maybe you have. Right, so hopefully that's okay. If you want to redo that, just rewind, have another go. And then let's try another one. By other one, I mean other 4, by the way. So I'll do the first one. So what this is going to be balanced. So basically the F1 D1 must equal F2 D2. So you just do force 1 times force 2. You can leave them in centimeters. It would be best practice, in an exam you would want them in meters. But I suppose centimeters is fine, it's up to you. So first one, so F1 D1, you basically, well, I'll do a proper example. So it should look something like this. So F1 D1 must equal force 2 times distance 2. So that's the clockwise moment being equal to the anti-clockwise moment. Then we just need to put our numbers in. So we've got 5 newtons and 20 centimeters. So let's just do 5 newtons times, I'll leave the units in just for this, 20 centimeters equals, and then force 2 is 10 newtons and we're finding distance 2. So that's 10 newtons times distance 2. If we leave it in centimetres, we'll get an answer in centimetres. If we convert it into metres, we'd get an answer in metres. So 5 times 20 would be 100 Newton centimetres equals 10 newtons times D2. You don't have to put the units in. I'm just doing it for this example. So as you can see, we have 100 Newton centimetres. This might be interesting just to see what the units do. We need to get D2 on its own, so we need to get rid of the times 10 newtons. So the opposite of times in by 10 newtons is divided by 10 newtons. Newtons cancel. Got 100 divided by 10. And 100 divided by 10 is 10 centimetres. If you turned it into metres, your answer would be 0.1 metres. Okay, if you want to attempt the next three, and then I'll give you the answers. All right, let's have a look at this one then. So 4 times 15, 60 Newton centimetres. Or you can convert it to metres, it's up to you. So that 60 Newton centimetres must equal F2 times 10. So it might look like this. So 60 equals force 2 times 10. So to get force 2, we need to get rid of the times 10, so divide by 10. So you should have 60 divided by 10, which would be 6 newtons. And then the same again. Hopefully you've got the hang of this one now. So 36, this would be 36 times 2 is 72. And then that one, the third one, which I'll just put down here. Third one would be 72 Newton meters equals force 1, which is 6 newtons, times whatever the distance is. So we would have to do 72 divided by 6, which would give you 12 centimeters. Again, if you turn it into meters, it'd be 0.12 meters. And then the last one, same again, so it'd be force times distance. So 2 times 100, 200 Newton centimeters. So I'll put this one at the bottom, so number 4. So F2D2 will be the clockwise, so that would be 200 Newton centimeters equals whatever the force is that's going anti-clockwise times 25. So to get rid of a times 25, we need to do the opposite, which is dividing by 25. So that will give you an answer of 8 newtons. Hopefully that one went okay after the first example. Let's do another question. So hopefully this one's okay now. Because they're both in centimetres, you can leave it in centimetres. In an exam, it's probably going to want metres. But we've got another exam style question coming after this one, so it's up to you how you do it. You'll get the same answer. Right, so let's go. Let's make our little table. So I'm going to say the sum of the clockwise moments must equal the anti-clockwise moments. So clockwise, we're going to take moments from our pivot. So it will be the weight of the beam times distance 0, which is 36. So I'm going to write weight of the beam, which is W0, times 36. And that'll be equal to the anti-clockwise moment, which is this way. So that'll be weight 1 times D1. Weight 1 times D1. Weight 1 is 6 newtons. Times distance 1 of 12 centimeters. So 6 times 12. So 6 times 12 is 72. So we would have the weight that we're looking for times 36 equals 72 on the right hand side. And then to get the weight, we just need to, we've got obviously the times 36 that's attached to it. So to get the weight that we're looking for, we need to do the opposite of times in by 36 and divide by 36. So we've got 72 divided by 36, which is obviously, there's a weight of 2 newtons. If you converted these centimetres into metres, you would get the exact same answer. So hopefully that one went okay. And then let's finish with one more exam style question. Right, so hopefully this one will be okay now. So this is an exam style question. So you have to pause and have a go, and then I'll take you through the answer. So I'm going to do a little table. And then we're going to do the same as before. So it's the clockwise moments must equal the anti-clockwise moments for it to be in equilibrium or balanced. So there's our pivot. So our clockwise is going to be the 1.5 times 200. So I've got 200 newtons times 1.5 meters. equals the anti-clockwise, which will be the force F that's being pushed down, times 3 meters. That's the distance to the pivot. Now, the units in these are both in meters. The only time you have to convert is if the units are different. So, for example, if you got 3 meters and 150 centimeters, you would have to convert the 150 centimeters into meters before you did the calculation. So we've got 200 times 1.5, so clockwise, so that would be 300 Newton meters, equals F times 3. So as you can probably see, this is pretty straightforward. We need to get F on its own, make it the subject, so we need to get rid of the times 3. So we need to do the opposite of times in by 3, which is dividing by 3. So 300 divided by 3 would give a force of 100 newtons. So that's the principle of moments. Clockwise equals anti-clockwise. Hope you found that helpful. Thanks for watching.